And hello everyone. Yeah, just want to before I start, just want to tell you something about where I'm putting some of these lecture notes. Okay, you can find them on GitHub, and what you need to do is just to follow this one called Singaporean Ramblings Nuclear Tech. This is the GitHub repository. If you're not sure how to download it, okay, and you don't code, okay, you can go to code and you just select this download zip, and you will be able to download all the files in this repository. So all this is hosted online, and you will be able to see lecture notes, or rather the notes I'm giving. Yeah, so don't worry about finding these annotations and drawings I have online. So I'm going to post a lot of notes or supplementary material there as well. So you can find them on that GitHub page. Just download it as a zip and you will be able to find what you need to find the notes. So, okay, yeah. So hold on. So anyway, we spent a lot of last time talking a little about waves. Okay, a lot of waves, and we're trying to talk about superposition and all this. These are hopefully not too complicated ideas. Um, and yeah, you might be asking, what does that have to do with nuclear physics? You will see that has eventually you should be able to find out as I go through this stuff. This is, I think, lecture 4. Okay. Eventually, I hoped to show you that everything in nuclear physics, or rather, lots of things in nuclear physics can be explained by this wave theory. Lots of things in nuclear physics can be explained by waves. Okay. Now, what do waves have to do with nuclear physics? Well, in nuclear physics, or at least a quantum physics world, you will see that things behave a little bit differently. And for example, an atom and electrons within atoms, they are governed by, well, they can only adopt specific energy levels. Okay, same goes for the nucleus. Okay, so one consequences of consequences of wave behavior. Consequences of wave behavior. Okay, electrons in atoms have discrete energy levels. Okay, protons and neutrons also behave the same way. Protons and neutrons in the nucleus have discrete energy levels. Energy levels. Okay, so these are the important things that I want you to take away if you forget everything I've talked about. So, okay, what we talked about last time was to highlight or illustrate the Young's double slit experiment. I may not get this interference pattern right for those who are more into physics, okay, but it is more or less this kind of thing. So the center spots will be the brightest, and then you kind of have less and less so-called constructive interference as we go out. And then in between them, there will be dark spots that are indicative of what we call destructive interference, where the waves actually cancel out. So now, yeah, what was done? I think Young's had his original experiment with light. However, when quantum physics comes into play, someone actually started firing electrons at this double slit and they observed this interference pattern. Okay, the funny thing about quantum physics, is that for this double slit experiment, okay, if you fire electrons one at a time, okay, electrons being particles, if you actually fire electrons one at a time, okay, what happens is that, this interference pattern is still observed. Okay, this interference pattern is still observed. Okay, electrons fired one at a time, one at a time, and you'll see this interference pattern. Now, someone tried to be clever, and he was trying to observe which slit this electron passed through. Okay, so someone actually put like a camera or detector. Okay, someone tried to put a camera or detector there to see which slit this electron went through. Now, once this detector came in, suddenly, for some reason, this interference pattern disappeared and you had two very bold lines. Okay, so in quantum physics, okay, the act of observation, okay, this is something quite cool. The act of observation changes the results. Experimental results. Okay, so that's something funny about the quantum world. Why it happens, I have no idea. I'm just going to leave it as that. But this is the observation. Matter just behaves like that. Okay, whether it's an electron or something else. Even protons and protons, they kind of behave the same way as well. So this is a very curious state of affairs. Okay, so yeah. Okay. So anyway, that's more or less Young's double slit experiment. I'm kind of hopping all over the place, but yes, how does this? Okay, so we established here that based on these experiments, electrons, protons, neutrons all behave like waves. Okay, in special circumstances. Okay, under special circumstances, protons, neutrons, electrons all behave like waves. In fact, most, if not all, subatomic particles behave like waves, and sometimes they behave like particles. It's just the world we live in. Okay, how does that correlate to nuclear physics? Okay, so I want to start focusing on energy levels. How do we get how this whole quantum effect gives us discrete energy levels. Okay, so discrete energy levels, these are something you will observe in the quantum world where an electron within a nucleus, within the atom can only have certain energy levels. The same goes for the nucleus. And that is what actually a lot of the time determines, okay, it determines well, it's one of the baselines for why some things undergo fission, some things cannot undergo fission, why things why nuclear reactions occur in certain ways, and even chemical reactions. They occur in certain ways because of this energy level phenomena. Okay, so let's just get to the part where waves result in energy levels first, and then let's continue on after that. Okay, so the key point I want to start us off with is that wave behavior results in discrete energy level. Okay, how does that occur? Okay, so the best way to understand it is to see what we call standing waves. So there's a lot of new terms I'm giving you today. Standing waves. So how to best visualize standing waves? Okay, so what we are used to is, let's say, a wave on water. This is a free wave. It is kind of a free. A wave on water is free to travel, wherever it wants. Okay, so if it's traveling to the right, this is what you will see. Okay, but let's say for example, I make it not free. Okay, I make the wave not free. Okay, not free. How do I make the wave not free? So if there's a way I can restrict the movement of this wave, what I'll do is that I'll make the ends stuck so that they cannot vibrate. Okay, so let me draw it like that. I make the ends stuck so that it cannot vibrate. Okay, so what I'm going to do is make the ends stuck. Stuck. So they cannot vibrate freely. Okay. Right, so let's say you have the wave and it still travels to the right like that. And then it's about to hit the right side. So once it hits this right side, what happens? Since this thing is stuck and we assume that the energy is conserved, it doesn't get lost to friction or whatever, it will sort of interfere with itself, and it will start going backwards. Maybe like this. Okay, I might be doing it wrong, but just want to give you the brief idea of what's going on. Okay, so the wave is going to go like this, go to the right, and then you go back and forth, back and forth. Okay, the wave bounces back and forth, and interferes with itself. Okay, so that's the idea of, a wave being stuck. Okay, so when it keeps interfering back and forth, you will sort of have an overall pattern, much like you have it on guitar strings. Okay, so just think of it like a guitar string or violin string. So guitar string. Okay, the best way to visualize what a standing wave is to look at guitar strings. So you have a string here, and what can happen? Okay, what can happen is that the string must vibrate. Okay, the string must vibrate. How is the vibration restricted? Okay, the vibration is restricted because these two ends are stuck. Okay, so you can vibrate it like this. Okay, you can vibrate it like this. So you have one so-called full sine wave, and then if it's vibrating up and down, you have something like this. Okay, so let's say, yeah, you can vibrate it like this. You can vibrate it in this one. You can vibrate it like this. But you cannot have like half wavelengths, right? Because the ends are stuck. Remember, the ends are stuck, so there's no vibration that happens at the end. So at the end, the amplitude is all, or the wave, the oscillations happen, or yeah, you cannot move at the ends. That is the restriction. Okay, so at the ends, the vibration is always zero. There's no vibration there. Okay, but in the center, you can have as many, you can have a certain number of, what you call, peaks and troughs. You can have a certain number of peaks and troughs. You can only have a certain number of peaks and troughs, and these are integer multiples, all right? Okay, these are integer multiples, or rather, let me do this in blue. Okay, so you see there is over here, there's only one so-called one vibrating thingy. Okay, so over here is where the peak and trough happens. Okay, and then here is where that peak and trough happens. And then in the picture number 3, you have 3 of these. Okay, I think we call these nodes. Let me go do a quick search on my other computer. Nodes and antinodes. Sorry. Okay, so nodes and antinodes. That was the correct physics term. So these things I'm coloring out for you now, these are called nodes, where the amplitude is 0. So the nodes are at the side, the end of the thing, or of the wave, and then the nodes are over here. All these peaks and troughs, these are called antinodes. Antinodes. So so what do these all have to do with energy levels? Okay, let's say wave number 1. Wave number 1 over here. Wave number 1. You can see that it has a certain amount of energy for the waves to like so-called travel back and forth. Okay, but the more intense the vibration, maybe the more ways that you can store energy. Okay, the more ways you can store energy. Okay, so you have a wave of, let's say the wavelength is over here is 2L, right? I think it's 2L. Okay, 2L. So if the length between these two fixed points is L, your wavelength here is 2L, then over here it's I believe wavelength here is 4L, or rather L by 2, sorry. This wavelength here is L. Okay, wavelength here is L. And of course you have more and more modes of vibration as you go up. So within this guitar string, so-called, there are multiple ways you can store energy, okay, based on the different wavelengths. Okay, so the more how do I put this? This is a okay. So each standing wave is one way to store energy, because waves, okay, the basic idea is that waves store energy. So you can store energy at different frequencies. Okay, you can store energy at different frequencies or wavelengths. Energy at different frequencies. Okay, assuming all of these are the same string, you can see that perhaps for wave number 3, it's of a higher frequency than wave number 1. Okay, for waves, the general idea is that higher frequency means less wave, a smaller wavelength. The formula here is V equals to F lambda, where the speed of the wave, assumed to be constant, is equals to the frequency multiplied by the wavelength. It's a basic physics thing. So basically, with all these standing waves, they actually represent different modes which you can store energy. Okay, and yeah, there are different ways you can store energy, but this energy or these wavelengths, they are fixed. Okay, these wavelengths are fixed. So you can store energy at different frequencies, but the frequencies at which, okay, frequencies, or let me put this down here, wavelengths, where you can store energy, is fixed. Okay, because of the restrictions you sort of place at the end here. Okay, so the way to understand the so-called particles, or rather matter at the quantum level, is to use this picture of a standing wave. Okay, these particles can so-called vibrate, but it's not really like a vibration, so to speak. But the easiest way to think of it is a vibration, even though it's strictly speaking not a vibration. Um, yeah, these waves, they so-called vibrate at different frequencies, and as you go up from, let's say, this, what we call n equals to 1, okay, n equals to 1, n equals to 2, n equals to 3, yeah, as you go up the frequencies, you have more and more so-called modes of vibration, and there are more ways you can store energy. Okay, so usually in quantum physics, the most basic quantum physics, you'll be dealing with a lot of standing wave equations. Why? I won't go too much into detail here, but you should just uh, just try to pick up. Okay, I may not be the best at explaining this, cause yeah, there's a lot more math that goes behind there, and how this all correlates to energy. You kind of have to study the equations. I cannot not go through math, but the long and short, if you want to skip the math, is just to get that. Okay, uh with waves you can store energy, but and with standing waves, okay, with standing waves, uh there are only fixed levels of energy which you can store, because the wavelength and the frequency is sort of fixed or restricted. Okay, why is this important for us? What does this have to do with quantum mechanics and so-called uh what do you call that? Yeah, so-called how the atom works or how the nucleus works. Okay, so this picture of a standing wave is actually what is similar to what a real nucleus is like, except it's very simplified. Okay, so let's say you have a hydrogen atom with one proton and then one neutron. Let's well, no neutron, sorry, one electron. Okay, let's just call this. Oh, this is very difficult to draw nicely. Okay, let's just have one electron that I will use X to represent. Electron and then one proton. Okay, so this is the hydrogen atom. Hydrogen atom. Okay, so there's one proton and one electron. So the proton is what? Positively charged, right? Positively charged. The electron is negatively charged. Okay, why doesn't the electron fall back into the proton? Okay, it is basically because of this standing wave thing. Okay, the electron's only allowed to vibrate at some certain frequency. That's why it's a sort of yeah, it's a quantum effect that prevents it from falling into the um, proton. Okay, so where do we see these so-called waves come in? Okay, where do we see these waves come in? Okay, the easiest way to understand is in terms of potential energy. Okay, potential energy. Okay, the way to understand it best is in terms of potential energy. All right, at least this comes into the picture. Okay, the electron will have some energy, but is trapped inside the atom because of the attractive forces here. So how does it look like? Okay, oh man, I have to write formulas. So okay, let's see. Let's have this picture. Okay, the force between particles is Q1 Q2 over 4 pi epsilon naught r square. Okay, why am I giving you this? Okay, basically what I want to say is that the Coulomb attraction, okay, Coulomb attraction, positive charges attract, is based on based on the charge. Okay, don't worry about using the formula. Just know that the force between two charged particles is based on the charge of each particle. The charge of each particle. And of course the radius or the distance between each particle. Okay, this actually governs the force between the particles and also the potential energy. So what happens here if we were to plot this out? Okay, so if we are very close to the proton, if we are very close to the proton, we'll have the least potential energy. Okay, so let's say this is x. Okay, x distance from proton. We will have maximum potential energy far away from the proton. Okay, and let's call this the energy. Yeah, maximum potential energy is far away from the proton, and is sort of a minimum closest to the proton. Okay, and then it's same for the other side, it's symmetrical. So this idea I hope is not too difficult. Okay, now the electron here has a specific energy. Okay, this specific energy is, well, let's say here is the electron energy. Okay, and this electron's energy is not enough to escape the proton. Okay, electron energy is not high enough to escape proton. Okay, electron energy is not high enough to escape proton. So what happens? So all this energy is trapped over here. It's trapped within this well, what we call a potential well, because this is potential energy. Yeah? Okay, this energy is trapped within this potential well. It's inside this electron, or rather, the electron has this amount of energy and is trapped in a potential well. Okay, and let's just call this E1 for example. And trapped in potential well. Okay, so this is the usual picture we will have when studying quantum mechanics, and then we'll have to do some math and kind of determine these energy levels. Okay, so the thing is that strictly speaking, if we have this wave picture, we will sort of have this vibration. Okay, so we have vibrations like this, and they will be restricted by how much energy this electron has, and of course these bounds here. Okay, they will be restricted by these bounds here. Okay, if we were to use the earlier picture, they will be restricted by these bounds here. And yeah, basically, if you have more energy, let's say here, okay, you will have more room to play with, and you can sort of fit more waves in here. Okay, I don't know exactly how that works, and I cannot do the math off the top of my head. Okay, but this is the basic idea between these energy levels, because the further you get away, the more energy you have, Okay, maybe I'm mixing things up now. Let me restart. But okay, before I even talk about different wavelengths and stuff, let me just draw some scenarios as to how this electron energy level can be done. Okay, you can have a wave of this n equals 1. We call this the fundamental mode. You can have waves where you can have vibrations of frequencies with shorter wavelengths, and we call these harmonics. Okay, harmonics. Okay, so with higher level of harmonics, you can have, like, more energy stored. Okay, so there is a little bit more complications, but you can see that this idea, hopefully you see that this idea of uh, waves, okay, and the fact that your electron has limited energy and it is less than the potential energy, this actually forms this restriction as to how the electron wave can travel. Okay, so the electron behaves like a wave here, and uh, the energy of the electron being less than the potential energy because of this Coulomb attraction, because of the attraction between positive and negative, that actually restricts the movement of the electrons. Okay, so let me write that down. Okay, so the electrons, first thing first, electrons behave as wave. Number two, movement of electrons is restricted. Movement of electron waves is restricted as electron energy is less than the potential energy required to escape. Okay, so okay, what I'm trying to say here is both of these effects combined give rise to standing waves. Standing electron waves. Okay, so this happens at the hydrogen atom. Okay, of course there are nuances there. I am kind of skipping over them, such as the fact that your electron nodes here, these standing wave nodes, they are not exactly zero outside this region. Uh, there's a little bit more complication with that, but uh, I will not go into that yet unless it's really important. Okay, this thing will become more important when we talk about alpha decay. We call that quantum tunneling, but I don't want to introduce too much at this point. Okay, I just want to give you the idea that this standing wave phenomena is important because electrons behave as waves, and the movement of these waves is restricted. Okay, so you can see, like, for a guitar string, you have a free as long as you have waves and then you kind of restrict the movement of the waves, we will have standing waves. Once we have standing waves, the wavelengths and frequencies kind of get restricted. Okay, and once you have that restriction, you have fixed energy levels. Okay, so I want to sort of summarize here. Once you have these conditions, once you have standing waves, the consequences, one, frequency and wavelength is restricted. is restricted. Okay, why is it restricted? Because the movement is restricted. Okay, the movement being restricted kind of impacts. Okay, it fixes the frequency or wavelength of the waves. Okay, and energy is directly correlated to frequency or wavelength. Or more specifically, a frequency. So therefore, energy levels are restricted. Okay, and energy is correlated to frequency, and because frequency is restricted by this movement restriction. Okay, this movement restriction. Now energy levels are restricted as well. Are therefore restricted. So anytime you have standing waves, all of these 1, 2, 3 apply. That means standing waves will imply energy levels are restricted. Okay, I'm kind of glossing over a lot of details, so the picture may not be 100% clear, and you might have to do the math in order to understand what I'm really saying here. But I want to skip the math. Otherwise, I'll be doing a full physics lecture, which I'm not really interested in doing in this video series. So pardon me if it seems confusing, but here are the main conclusions as a result of all that math. Okay, once you have standing waves, your energy levels are restricted. That's what I'm trying to say here. So what is true of electrons is also true of the nucleus. What is true of electrons is also true of the nucleus. Okay, one is that protons, neutrons behave as waves. Okay, movement, number 2. Movement of proton-neutron waves restricted by attractive forces. Okay, restricted by attractive forces. In the nucleus. So earlier we see that the attractive force between the proton and electron, it creates an energy barrier, so to speak, that prevents the electron from just flying off. The same applies in the nucleus. Okay, the same applies in the nucleus, except instead of electrostatic force, we have the what we call the strong nuclear force. Okay, so this is what we call strong nuclear force. Strong nuclear force. Okay, so the strong nuclear force is superbly strong in comparison to the electrostatic force, okay, or electromagnetic force, if you want to be more, complete. But over here is electrostatics. Okay, the strong nuclear force is about 1,000,000 times stronger, I think. And just to give you a rough idea. I may be getting the math wrong, but yes, it's a lot stronger. Okay, but the same principles apply because protons, neutrons behave as waves. The movement of proton and neutron waves are restricted by these attractive forces, such that the protons and neutrons, while they have energy, it is less than the potential energy needed to escape. Okay, so there is some sort is a little bit like this picture here. It's a little bit like this picture here where your protons and neutrons will have some energy. And technically speaking, again, because of quantum effects, they cannot have zero energy. Okay, they have to have some energy, and um, but the energy is not enough for the proton or neutron to escape. Therefore, they have this sort of standing wave within the nucleus as well. So these effects give rise to fixed energy levels within the nucleus. Okay, same idea as well. These give rise to fixed energy levels within the nucleus. Okay, a common thing you will see in quantum physics is that most of the times you will see that energy levels are always in some sort of fixed or what we call quantized amounts. Okay, they're of a specific quantity. So we like to call this energy is quantized. And that's where the word for quantum physics come from. Energy is quantized. Okay, which basically is a fancy word for saying fixed energy levels. Okay, I hope this picture sort of stays in your mind when you start thinking about nuclear or quantum physics. Okay, because of wave behavior. Okay, because of wave behavior and the fact that you are restricting the movement of these waves, the energy levels are so-called fixed. Okay, hopefully you see this picture more conceptually rather than with all the math. Okay, but of course with all the math you will actually have a much better understanding of what's going on. Okay, if you are interested in the math, which I suppose most of you aren't, but if you are interested in the math, okay, go read up. Okay, on what we call the Schrodinger's equation. Yeah, Schrodinger's equation. And number two, you should read out on something. Okay, this is kind of related to the Schrodinger's equation. You need to read out something called the wave function. Okay, this is what we call psi of x. Okay, and that determines the so-called wave behavior, or that's a mathematical way of describing the wave behavior of the proton, neutron, or electron. They call this the wave function. And these are the better way to describe them is that these wave functions, they describe the probability. They are probability waves. Okay, probability waves. Or maybe that's sort of inaccurate, but that's closest concept you can get. These are probability waves. That means these waves will impact the probability that you'll find the electron or neutron or proton somewhere there. Okay, these are determined by the wave function. So the probability is technically not the wave function, but the wave function squared. Psi squared, psi x. Okay, this is the Greek letter psi. Okay, we call this psi. Okay, so the probability is governed by psi squared. Okay, or rather the more if you really want to be technical, it is the wave function multiplied by the conjugate of the wave function, because these are complex numbers. Okay, so the conjugate, this will form the probability. So I'm not going to go through this. These are very technical, and this lecture is not meant for technical audience. Okay, but I just want to roughly bring across to you the key ideas as to why we think, at least in terms of the math and the physics, why the electrons and neutrons and protons behave in certain ways. And this idea of waves, the fact that they behave like waves and particles, this this lays the groundwork for almost everything in nuclear physics. Okay, so this is kind of the prerequisite understanding you must have in order to start understanding nuclear physics, fission reactions, and so on and so forth. Okay, whether the neutrons will they fuse with the nucleus, or will the protons fuse with the nucleus, and so on and so forth. Okay, all of these have very heavy reliance on the fact that these particles actually behave as waves. And then because they behave as waves, there are certain consequences as to how these particles will behave, and that will give rise to why nuclear physics is the way it is. Okay, so how does it get back to the fission reactions and so on and so forth? We'll probably have to deal with that next time. But thanks for watching.